Welcome back to the Marine Hydrodynamics course. So in our last class we talked about what an ideal fluid flow is, and yeah, that's all we talked about. And I also told you that we'll be discussing about what vorticity is and how can we actually explain what is happening with your sink basin, etc., or wherever you see vorticity, which could be in tornadoes or wherever. So, but before we move on to vorticity, we want to explore another mathematical concept which I believe you might have seen earlier, which is circulation. So, let's say we have a closed contour, or let's say, in fact, that we have a vector field. Now, of course, vector field is nothing but you can consider this as, let's say, now we have defined the flow and we have a vector field of this sort. So we have, let's say, solved our problem and we have a vector field of this sort, and I'm not going to waste my time drawing arrows, lots of arrows, but you can assume, let's say, the field goes from here to here and something like that. So this is some kind of field, and these are actually individual arrows, but I'm not denoting them right now. And this could be something like this could be something like this, and so on. And let's say I take a circle at this point, right? So this is my curve which I am taking at that particular point, and then I have the velocity at each point v, and the small distance which I move is dx. So if I do a circular integration v dot dx, this quantity which I get, this mathematical quantity which I get, denotes the circulation. So this denotes the circulation, and we have different formulas to calculate circulation, but we won't go into that currently. But we just want to understand what circulation is, because this will help us to build on the concept of vorticity. So circulation, nothing but, suppose you have a vector field or anything, and if you carry out the circulation at a particular material curve, right? So that will give you an idea about how the fluid or any particle, if you drop any particle there in the vector field, how will it react to it, how will it go in a circular way or not. So that value is denoted by circulation. So if you get the value of circulation as 0, then the particle won't actually go in a circle. If you get the value of circulation as positive, it will go anti-clockwise. If you get the circulation value as negative, it will go in the clockwise direction. So that is the idea of circulation. And then using this concept, we'll build upon what vorticity is. Though vorticity and circulation are closely related, but there's a subtle difference between them. So just talking about circulation is denoted with this symbol. It's a fancy symbol known as capital gamma. So capital gamma is equal to integral whole curve v dot dx. So this is the tangential velocity. We are integrating it through the whole curve. So that gives us the circulation. And another point, that circulation is an Eulerian idea and it's an instantaneous snapshot. So suppose you have a fluid flowing and you just have a camera and you take a snapshot, that will give you this kind of a pattern. So that is what circulation is all about. And from this circulation we have a very important theorem in fluid dynamics known as the Kelvin's theorem. Kelvin's theorem, and I'm going to write that as KT. Don't confuse this with the kinematic transfer theorem, because that was KTT. This is Kelvin's theorem, KT. And what Kelvin's theorem says, that the change in circulation with time is equal to 0 following any material contour. So any material contour is this, any curve which I choose is a material contour. So what Kelvin's theorem says, that for ideal fluids under conservative forces, so for an ideal fluid under conservative body force, we must have the change in circulation as 0. So this is what Kelvin's theorem state. And what are the repercussions which we have using this? So using this, we can say that for an ideal fluid under conservative body forces, so I'm going to acronym that as IFCF. So this is ideal fluid under conservative body forces, IFCF. So for IFCF, linear momentum, so we'll have linear momentum which can change, of course. I just give a push to a particle, increase its velocity or something, so it's velocity can change, so linear momentum can change. Then we talk about the angular momentum. So angular momentum, of course, gives you a sense of how the particle is rotating about a point, etc. So the angular momentum in this case cannot change. So this is the important thing to note of: the angular momentum of an ideal fluid under conservative body forces cannot change. So this is what Kelvin's theorem says, and this we can prove it mathematically, but we don't really care about the proof right now. We just want to see what the concept is. So the angular momentum of an ideal fluid acting under conservative body forces cannot change. This is by Kelvin's theorem. So this is one thing to note about. Then what we have is certain ideas. So I have told here that the angular momentum cannot change. This does not, however, mean that the angular velocity cannot change, because suppose I am calculating the angular momentum. Let's say this is body m, this is point O, and this body m is going at velocity v1, and this distance, let's say, equals to x. So the angular momentum I can write as mv into x, or let's say this is r by convention. So the angular momentum I can write as mvr. But by conservation of angular momentum, this means that if the distance between the mass m and point O shortens, that would mean r shortens, but for the conservation of angular momentum, the velocity must increase. So the angular velocity can increase, but the angular momentum has to be constant by Kelvin's theorem. Okay, so this is all we had, and now let's finally move on to vorticity, the talk of the day. So let's just scroll down. Okay, so we'll talk about vorticity. So mathematically, vorticity is defined as omega vector is equal to the curl of velocity. So you'll have the velocity function, the curl of that velocity is vorticity. And we can of course expand this mathematically as del w by del y minus del v by del z I cap minus del w by del x minus del u by del z j cap plus del v by del x minus del u by del y k cap, right? So this is just mathematically, I'm just taking out the curl of the velocity, and you have the delta in a matrix form, and then you can just cross product that with velocity to get this equation. And what can we take from this? So from our circulation which we saw earlier, we know that circulation equals to integral v dot dx, and by Stokes theorem, if you remember, we can write this as double integral curl of velocity dot n cap ds, and curl of velocity is nothing but vorticity, which we just saw now. So I can write this as omega dot n cap ds. So okay, and this if you look at it carefully, this is nothing but we are integrating the vorticity in a whole area. So suppose I have this surface, so I'm integrating the vorticity at each point, I'm adding the vorticity at each point to get the net vorticity at this surface, and that will give me the flux of vorticity out of the surface S. That will give me the flux of vorticity out of the surface X. So that is what actually vorticity is. So the main difference between the circulation and vorticity is that the circulation gives you an idea about the system, how the system is rotating about a larger region, about a macroscopic region. So you have to integrate over this circular point, like about this curve, to get the circulation inside that curve or around that curve. But what vorticity does is, vorticity tells you the tendency of each and every particle to spin around. So vorticity is actually calculated in each and every point. This curl of velocity gives you the spin at each and every point. But whereas circulation is more of an average phenomenon, it simply gives you at a macroscopic level, and vorticity is at a microscopic level. You can think of this as that. So that is the main fundamental difference between circulation and vorticity. And coming to that, there's one more mathematical logic or equation which you need to take care of. So I'll just go to the next page, and the mathematical thing which you can take care of is vorticity is directly proportional to 2 times the angular velocity. So this is a mathematical equation you can keep in mind. So vorticity is proportional to 2 times angular velocity. Again, we can prove this using some simple maths, but we don't really care about the proof now. So vorticity is proportional to 2 times angular velocity. And another point to note is the new concept of irrotational flow. So we have previously seen what an ideal fluid flow is. Now let's see what an irrotational flow is. So a flow is irrotational if the vorticity is 0 everywhere, or if the circulation is 0 along any arbitrary closed contour. So suppose you have an arbitrary closed contour. If the circulation around this contour is 0, then you can say it's an irrotational flow, and if the circulation is 0, then of course the vorticity at all the points will also be equal to 0. So that is what irrotational flow is. And by Kelvin's theorem, we can say that the change in circulation in an ideal fluid acting under conservative body forces must be 0, and therefore once a flow is irrotational, it is always irrotational. So once a flow is irrotational, so I'll just write that this as once irrotational implies it's always irrotational. Right, so this is only when for an ideal fluid acting under conservative body forces. So this is the concept of irrotational flow and the concept of vorticity. Now we'll dive more deep into vorticity and try and derive out several other equations as well. In our next class, we'll see what is vortex lines, what is vortex ring, and we'll actually see a visual representation of it, so that it clears out and makes our concepts better. So till then, stay safe and thank you.